Hello friends. So in the continuation of CTQ series, we will see the CTQ 11 in this video, and there are a lot of things to calculate. I have given here. First, we have to mention the polarity of the op-amp to avoid the positive feedback mechanism, or I can say to keep the circuit in the negative feedback configuration. Okay, so this is the particular structure. What we are doing, we are having some reference input on this terminal, and we are having this feedback from output to input through this. So we have to see that for what particular polarity the input is, what I should say, for particular polarity, this system is in negative feedback configuration. Okay, so the other thing is that if there is a small perturbation in the VREF, what is the effect on the output? Simply, I want to see the gain. If on this terminal, we are giving some small signal on top of that V reference, and what is its effect on the output? Simply means we have to calculate the gain. Okay, so simple, the negative, we are in the negative feedback system, so what should be the gain? We can calculate it easily. Okay, so how much supply noise suppression is there? So supply noise suppression means we'll simply apply some perturbation in the supply because we want to see the effect of that supply perturbation in the output, and exactly this factor particularly should be if we'll see the gain should be from supply perturbation to the output should be high enough. It means that or we can say it should be low enough, because any particular perturbation in supply, if it is reflected on the output, then we can say we are having directly this supply noise effect on the output. Okay, so if this gain from the supply noise perturbation to the output, if this gain is very small, it means for particular input perturbation, we are having less effect on the output. We can say this way. So this is nothing but a supply rejection. Okay, supply noise rejection. Okay, so we'll see what is the polarity. Okay, what should be the polarity? Let's consider this as a positive and this is a negative. Okay, so what will happen if this particular value of voltage increases, means this node is increasing. So what is happening actually, this VD is a difference voltage is reducing. If difference voltage is reducing, this node voltage is reducing. Okay, what is this node voltage that I call as X? So what is my Vx node? Vx node is nothing but A times your difference voltage. Okay, so if my difference voltage is reducing, Vx is reducing. If Vx is reducing, what is happening for this transistor? The VSG is increasing, and if VSG is increasing, ID is increasing for this transistor. And if ID is increasing, then what is happening? Because ID is flowing through this resistor R, so ultimately if ID is increasing, this V out is increasing, because V out is nothing but simply ID times R out. Okay, so it is ID times R out, so we can say, so V out is nothing but ID times R out. So what we have seen, we started with an increase in this voltage value, and we are getting again the increment in this value. So what it means to say, we started with an increase in this node value. So decrease in this VD means decrease in the node X values. So VSC increased. VSC increased means current increased. Current increase means this IDR drop increased means V out increased. So ultimately, with an increasing, we are again getting increasing. So it is nothing but a positive mechanism, positive feedback mechanism. So it is nothing but positive feedback mechanism. So what we can say, this is in positive feedback configuration. Okay. So for the negative feedback, what should we do? We have to simply reverse the polarity, and we can analyze it also. If we are reversing the polarity and same connection is there, then again we can consider it. There is a increment in this output voltage, so this incremental voltage is fed to this feedback. So what I mean to say, again we should consider the same way. Let I'm increasing this voltage, so this voltage increasing means this difference voltage is reducing, difference voltage reducing. Now the sign is means opposite. Difference voltage is reducing simply means this voltage is increasing, Vx is increasing, so Vsg is reducing, Vsg is reducing, hence Id is reducing. Id is reducing means this particular drop, which is nothing but IDR, is reducing, so this node is reducing, hence it is in negative feedback configuration. It is negative feedback. Okay, so this is our target to get the negative feedback. Now our polarity is fixed. Okay, if so now we want to calculate the gain. Our polarity is fixed, so this is my gain, negative, positive. This is vref, and say v out. Okay, so instead of r1 I should write r only, because we are using r. Okay, now what I want to say, if I'm applying a small signal perturbation here that I call del V, let's say del V in, I want to observe del V out. Okay, so for particular vref there is a common mode set at the output, which is nothing but equal to this what I should say, it is nearly equal to the vref only. Okay, so actually I should mention here, vref is what, common mode voltage. It is also setting output common mode voltage at input. Okay, so output common mode is what, output common mode is also equal to vref if a is infinite. Okay, for the finite gain the common mode is little, means far, a little far, not much far, but a little far from the vref, that we can see. Okay, so because only this virtual short is applicable means vref is also applicable on this node, which is the output common mode as well. Okay, so now on top of that common mode, the V reference, we are applying some perturbation V in here, and we want to see exactly the output change, that is the del V out. Okay, so if I'm applying del V in here on this node, what we are seeing here, let's say okay, so if you are applying a del V in here, so what can be this value at this node, and accordingly we'll calculate value at this node. Okay, yes, so what we are seeing here, simply just for from the common mode point of view, we knows that if virtual short is applicable, then this way will be the this way will be the answer. Directly common mode we can see. Now if I want to calculate a small signal gain, if you want to calculate the small signal gain, then what it will be? For a small signal gain you can just short the DC, and DC short, and DC short is there, but you applied a signal. Okay, so there should not be any confusion. Okay, so a DC short but signal is there, this is my del V in. Okay, and other way also we can write, if DC shorted we will not write write like this, so that other cannot confuse here. The point here is that I can mention it as the voltage source perturbation, and this DC which was previously available, Bref, this is now shorted, this is now shorted. Okay, so overall what we can say, there is a del V in is applied on this input. Okay, so what I can say here, let this node is at del V out. So what is the this node x value? So I'll say Bx small signal is nothing but del V out minus del V in times A. So this is the this node voltage. So what to speak of this transistor, let's say M naught. This M naught transistor is nothing but a common source configuration. So M naught is in common source configuration. For the common source, there is no loading because current is zero. If no loading is there, directly we can see. If even if there is a loading, we will see this side impedance. But as this side impedance is infinite, so we are not worried about that. So directly we can say what is the gain from X to out. So del V out equal to minus GM naught times R parallel RDS naught. This we knows times del Vx, or I should say the small signal Vx. I can also write del Vx. So minus GM naught, as I can consider R is much smaller than this RDS naught. Let I consider this assumption. Okay, and what it is? It is del Vx is what? Del V out minus del V in times A. So what I can write here? I will write here del V out will take on the one side, which is nothing but 1 plus GM naught R equal to GM naught R del V in A here. A is also here. This term is also A. Okay, because A is multiplied here. So what we write del V out by del V in is simply 1 plus GM naught RA divided by GM naught R. So it is happening like that. So is there anything missing or everything is right? Del V out. The common source gain is minus GMR times Vx, which is nothing but del V out minus del V in times A. So it will go here del V out by del V in. Okay, so I think this is should be reverse. I have written incorrectly, so it should be reverse. So what is the gain? Okay, if my gain is infinite, then what you can see del V out by del V in is equal to 1. Okay, so it is actually unity gain system. So it is a unity gain system. Anyway, so we have seen polarity. Now polarity is correct, and we have seen this calculation. Okay, so this is the one thing. Now I want to make some change here. Let I'm using NMOS here. Let I'm using NMOS here. Then first of all we have to like find the polarity, then gain. So for finding the polarity, if I'm using the NMOS, simply we have to reverse down the polarity. It means to say if I'm increasing this node is increasing. So overall, VD is reducing. If VD is reducing, means this node is reducing. And if this node is reducing, ultimately I can say this VGS is reducing. Hence the current is reducing. Current is reducing means this node is again reducing. So hence it is a negative feedback. Negative feedback. Now we want to calculate the gain for it. Then what we'll see, the incremental diagram I want to plot here. Here I am applying an incremental source, which is this time I am writing just V in, not del V in, but V in only, because this is an incremental source I am applying. So no need to write del V. So if I want to calculate this gain, then what we can say, we can directly say. So this is node. I am considering this node as V out. They all are incremental voltage. So what is the X? So Vx is A times V in minus V out. I think in this diagram something we have, okay, right. Yes. So it is Vx. So what is the V out now? From V out to from Vx to V out, what we are seeing, it is a common drain or source follower. So we want to calculate the gain from X to V out, and what it will be. Usually, what is the effective GM for this structure? Let I should say first thing I will tell, this is not, it is not loading. It is 0 ampere going this side. So I want to calculate the gain of individual this structure, which is nothing but common drain. So all of you know what I am taking. This is my Vx. This is ground, and this gain I want to calculate. So first we will see what is the GM, and what is the R out, and these two are giving me nothing but gain from V out by V. Okay, so first we'll calculate the short circuit transconductance. For this, here Vx is applied, it is 0. Here I want to short it, ISC. So what is the short circuit transconductance? That you should see only one device is there. So this ISC is nothing but GM Vx. Okay, no other component. So ISC by Vx is GM, which is nothing but GM of the structure. Short circuit transconductance we can see here. Okay. Now, if I want to see the impedance looking at this node, what is the output impedance looking at this node? So this is the short circuit transconductance. Now we will look the calculation. We will look for the calculation of R out. So now point is that is this exact a correct way to calculate this? What I should say R out, or there should be something on this gate. This is the point. Because what is the previously connected here? If I am calculating the R out, what is connected here? This gain block is here. Okay, and here let this voltage 0 first, so I cannot directly calculate the output impedance of this MOS. Okay, so actually here I oh no problem. Of course I have considered Vx here, but exactly if I want to calculate the gain from V out to Vx and whatever the point, I want to calculate the output impedance at this node R out. Okay, what the GM we have seen. Is there modification in the GM that we can also analyze from here? Okay, so from the short circuit point of view, the GM will not change. Why GM will not change? Because what we are seeing here, okay, let's see, we'll see the GM and all this term for the transistor again. Okay, so let I should do the calculation again. This calculation from the GM is not that exact because we are having the gate connected to the this gain block as well. So when we will do the GM calculation, so GM calculation and R out calculation. Okay, so both the calculations will give me direct input to output gain. Okay, and then we'll see if we are separately calculating the gain, then what will be the effect. If I'm calculating the Vx individually, then I'm going to the output, and if I'm calculating for complete block, I'm GM and the RDS. So individually we'll calculate both the things and we'll match the result after that. Okay, so what is the point there? So if I want to, this is my small signal Vin. If I want to, sorry, as I'm using the NMOS here. So I think point is clear. What is the thing I want to tell here? I want to first calculate these two things directly for the entire block. This is my R. This is the short circuit terminal. ISC I want to calculate. Okay. So this terminal is grounded now. This is ground terminal. So what is the Vx value? Vx is nothing but A times V in minus 0 because output terminal is shorted. So A V in, this is Vx. Okay, so now what is this ID current? ID current is GM of the transistor times Vx, GM naught I should say. So GM naught, what is the Vx? Vx is A V in. So what is the transconductor? This is only nothing but ISC. So what is the ISC is GM naught AV in. So what is ISC by V in is nothing but short circuit transconductance for the complete structure, which is nothing but GM naught times A. Okay, so our gain, this gain block is modifying my transconductance for this structure. So I can say voltage to current converting capability of MOS is enhanced by the gain block. Okay, so this is the actual definition of transconductance. So what is the transconductance? It is nothing but voltage to current conversion capability of a transistor. Higher the GM, better is the voltage to current converter. Okay, so by applying this block here, we are just enhancing the current voltage to current converting capability of this amplifier, or simply we are boosting it by this gain factor A. Okay, so in other word, I can say we are boosting the gain or boosting the transconductance. So we are boosting the voltage to current conversion capability of MOS. Hence, it is also known as gain boosted structure. Gain boosting structure. Okay, because we are boosting the gain, whether it is a current gain or voltage gain, we will see here we are increasing the or we are boosting the transconductance by the factor. Actually, the transconductance for the block is this, but we are boosting it with the gain factor A. So this is the net looking transconductance for the structure. So it is boosted. Okay. So my point is not that. For the complete structure, now we have seen the calculation of GM, which is now boosted. Boosted means with the factor of A. Now we want to see the exactly output impedance looking at this terminal output node. So when we calculate the output impedance or any impedance, we usually short the input. This is my R. So what I will do, I'll apply a test voltage, which I call VT, and I'll observe my current IT. Okay. So first of all, what is this node X? Let's see. What is the current in this resistor? This current, first I will write it IR. What is the current in this? This I will call ID. What is the current in this? I will call 0. Okay. So what is exactly my IT? My IT is nothing but IR minus ID. This is my one equation. Okay. So what is my Vx? My Vx is nothing but 0 minus Bt times A, which I also call minus ABT. This is my second equation. Now the thing I want to calculate here, what is ID? I told this thing many times. When we write the expression of ID is simply for any particular transistor GM VGS plus GMB BBS plus GDS BDS. Okay, so what we are seeing here, the source is at the VT and drain is at ground, get it as Vx, and body is also ground. That I should say body voltage to 0. Okay, what is happening? GM, what is the gate? Gate is at Bx and the source is at Vt. What to speak of GMB? It is body at ground, so only minus Vt. What to speak of BDS? BDS component drain at its ground, so minus BT. So what I can say, this IT. Okay, so ID is what? ID is minus GM, or better to write here. What is the ID? ID is minus GM plus GMB plus GDS times BT plus GMBX. This is my ID. Okay. And what is the VX we have seen? VX is nothing but BX is minus ABT. So what is the ID then? ID is nothing but one approximation I should consider here. Approximation is that GM is much greater than GDS. Just I am telling this all the times because I want to write the equation correctly. When we are considering the body effect or not considering, we will ignore after that. But at least we should write it. This is also greater than. GMB. So for the time being, I'm ignoring them. And what is this? ID is minus GMBT. And what is this? Minus A GMBT. What exactly I'm getting? I'm getting 1 plus A GMBT. This is my ID. And what exactly the IT is? IT is IR, which is nothing but VT by R, and minus ID. So minus ID means plus 1 plus A GMBT. So if I take the BT common, what is happening here? 1 by R plus 1 plus A GM. So let's say A is much greater than 1. So this expression can be written as BT 1 by R plus AGM. So I can write BT by IT as 1 upon 1 upon R plus AGM. So what we can consider here, let A is much higher because A is very greater than. So what we can see here, one more approximation, that A is much greater than 1. So I can consider 1 upon R as much smaller than AGM. So what this expression will reduce to, it will reduce to 1 upon. So now what we got for the complete structure, this is my complete structure. Whether it is a gain boosting or not, I will not consider this thing. But yes, here I am applying my input. Here what is the mechanism happening here, I don't care. And here I am getting my output across the register R. Okay. So what I got here, GM I got GM naught times A. GM got modified. GM got modified, yeah. GM times A. What I got R out, R out I got, and upon A times GM naught. Okay. So what is the gain? Gain here is, we will see GM R out. So it comes exactly 1. Why I say approximated 1? Because it is nearly 1. With anyway, we are using the voltage follower. Okay. Anyway, we are following. We are using the voltage follower structure. Okay. But what we have seen that current to voltage conversion capability is increased, and this particular capacity of this structure can be used somewhere in this structure or by the previous structure. This is my V in. This was my previous structure. If we see for this structure, we can have the advantage because here we have the gain stage is the common source stage, and previously is the boosting stage. So this is the boosting stage. Boosting stage. So for this structure, we can also analyze. Let I put. I should put this particular structure in the box. Okay. Let I should put this structure in the box. Then what I am able to see, I am able to see again a box. Whatever mechanism of the gain is here, I don't care. But here I have input and I am taking output across this load. Okay. So there are many more modifications here. I'll use a cap as a load instead of R, and we'll see the effect. And other way of calculation, that is the individual calculation that we have done for this structure, will again match for the direct analysis of gain in this way, GMR out. So in the next video, we will see the calculation for the complete structure GM and complete structure R out, and accordingly we will proceed for the solution. Okay. So this is enough for this video. We have seen a few things here. So one thing that I was applying here, you need to look for it whether you can directly apply for the individual structure or not. Is there any problem while we are calculating the GM and R out for the individual structure, and we are simply multiplying with the previous stage gain? then is there any problem, then we can see. Okay, so I think this is enough for this particular video. In the next part of the CTQ 11 we will see other things and very interesting things we will see. Okay, so thank you.